we typically use this unelastic approximation. But we go, as Uli said, for Earth, we go a step further, and we use what is called the Boussinesq approximation. And that is based on the fact that these two gradients, so the temperature gradient in the background state, and also the density gradient in the background state are, well, say smallish. So for Earth, it's something like 0.2. So to Mars is saying 0.4, but it depends on at which depth you actually look for Earth. So an average is more like 0.2, I would argue. And therefore, for Earth, typically people use the limit that they say, okay, dissipation number and co-density parameters, so the temperature gradient of the background state and the density gradient of the background state are supposed to go to 0. That means you have a flat temperature profile, or the adiabat is flat, and also there is no density variation in the background profile. That you may argue that is not a very good approximation because 0.2 is after all not that small, but this has considerable advantages concerning your simulation, so it simplifies them a lot. And well, I mean, I think somebody should look at what is the difference that such a approximation actually does to your dynamic simulation. And as I understand, Tamar is planning to look into this, or you can contribute to that as well, because both options are in the code. So you can either use this equation, the unelastic approximation, with where you allow for that background density stratification, or this where you actually say density is the same everywhere and the ideal is actually flat. Okay, so with this approximation, basically, as we said, so we're looking at this. This was the unelastic, right? And now we say that the gradient in the density vanishes. So we just end up with this term. So we say divergence of the velocity equals 0. And this is the effect of the Boussinesq approximation here. Another effect is that actually viscous heating and ohmic heating can be neglected. That is not so easily to be seen, but basically they are of order of the dissipation number. So if you say the dissipation number goes to 0, these two additional heating terms go to 0. And remember, they were in the energy equation or heat equation, they appeared here, these two terms. Okay. So that's, again, part of the Boussinesq approximation. Now, you do that, and then you can write your Navier-Stokes equation in this form, which doesn't look too much different. But now, basically, what we have here, this is just the first order disturbance around the background state. So the background state, there was no velocity. So it was hydrostatic, right? So no velocity. So this is the first order disturbance here. And now this rho, I multiply this with, is the background state. So this is 0 order, this is first order product is first order. This, you may say, is second order. So maybe small, unless basically velocities become large. So P prime is now the first order disturbance. So this is, we subtracted the hydrostatic state. So this is total pressure plus the plus centrifugal terms, as Uli told you, minus hydrostatic. So this is a non-hydrostatic term we're looking at here. So this is first order. This is first order denoted by the prime. So the temperature gradient now is, this is the first order temperature gradient, and the background is flat, as I said. That's subtracted here already. Lorentz force is first order, and then you have here first order. So background density profile times first order velocity. Okay, so this is now the first order disturbance of the background state we're solving for in actually. And this, as I said, is the Boussinesq version of this equation, and there's also an unelastic version of this equation that you can choose. Okay, then the next step is, as Uli said, we go to non-dimensional quantities. And as I already said, there are two different schools. Like Gary Gutwein would never do this. People always do that. And there are basically two reasons for doing that. One reason is, as Uli said, so you try to rescale your quantities such that all terms, or without a prefactor, are of the same order of magnitude, or comparable order Numerically, this certainly has an advantage, right? So because one term cannot dominate the other if you scale them correctly. Right? So you don't have issues with the precision, and the precision does not allow to resolve one term which is too small because of your rescaling. So, and what we do, Oli already said that basically we use a root scaling, where basically the length scale, or any length scale appearing, is now measured in terms of the thickness of your shell. So outer radius minus inner radius. So then you make the transition, length, any length radius or for the outer radius is, represented by R times D, where D now is your measure. It's not meter anymore, but it's thickness of the scale. And then this is dimensionless, the R, if you make that transition. For the time, as Oli said, it's the viscous diffusion time. So the time that any disturbance in your flow is transported simply by viscous friction. That certainly is a very long time. I may argue that this is not a very good choice, but that's the choice we do. And then temperature is scaled by something like the temperature jump. So outer temperature minus inner temperature, or the other way around, inner is hotter. So that its delta is supposed to express the difference inner radius to outer radius. And then the magnetic field has this a little bit peculiar scale, which actually makes the non-dimensional be here square root of the Alcifer number that we introduced, but we can also talk about this later again. So this is a bit peculiar scale. And as Uli already said as well, there are different ways of rescaling, and there is no perfect recipe to do that. And sometimes we actually write about different scalings in our paper. So one paper has a different scaling than the next paper. Magic is always the same. But after we have the results, we can actually apply different scalings. We can actually convert this again to kilometers we want by using D, which is appropriate for Earth. So we multiply the non-dimensional R with D, and then we have something which is appropriate for Earth. Or we can use D for Jupiter, right? Or we can use D for something else, right? We just have to rescale by giving it a different D. So this is certainly one advantage of non-dimensionalization. So you have one simulation, and then by rescaling it, you can apply it to different problems. And well, another advantage is that if you then plug these transitions in, so you make your scales all scale dimensional, and you can start to actually collect all these different quantities to as few quantities as make sense. So for example, here, right, we have only 1 over Ekman number in front of the Coriolis force, Rayleigh over Prandtl in front of the buoyancy, and 1 over Ekman and PM in front of the Lorentz force in this particular rescaling. So basically, you may say there are only 1, 2, 3 factors, additional factors that we have here. And this is an advantage because now we talk about ratios of physical properties. And this equation tells us that it's not, for example, viscosity in itself which is important, but it's the ratio of these dimensional parameters which scales, for example, buoyancy. That is to say, of course, in a certain dimensionless formulation. But that tells you more about the physical background or the numbers which are truly important, right? Hopefully, if you choose rescaling correctly. Okay, and then the remaining equations, we just talked about continuity and Navier-Stokes so far, and energy is basically this, divergence of U vanishes. Well, this is actually the continuity equation in the simplified form with the Boussinesq approximation. Then divergence of B, of course, vanishes. Then the dynamo equation that Uli introduced. And then basically this is now left over of the energy equation. You write this now simply as changes in the temperature disturbance when you have subtracted the constant temperature of the background state. So these 4 plus this equation, this Navier-Stokes equation, is the equations that we saw in the Boussinesq approximation. The code actually, as I said, allows for an unelastic approximation, So you will have some additional terms which deal with the gradient in the density, background density state, right? But that would be too much of a complication now. And then Uli already introduced these dimensionless numbers that appear here, so Pm, Pr, and so forth. So now, if you collect all the dimensionless numbers left over that actually control now your code, these are just 5. And you throw in 11 different properties. So you throw in viscosity, rotation rate, shell thickness, thermal expansivity, gravity. For example, here normalize at the gravity at the outer boundary. That's why I go for outer. Temperature scale, some temperature scale. Here CP, kappa, the thermal diffusivity. Here again, magnetic diffusivity. Or actually, this is now the aspect ratio. So inner radius divided by outer radius. So now you see by collecting all these 11 different properties, you can reduce it to 5, and you think that, or hopefully these 5 are the really true characteristic quantities that will quantify or classify your problem. So this is the input you need for matching. Okay, well, now we basically, if you now look at the number of equations we have 9 equations for 8 unknowns. So we have, so these are 3 equations because it's a vector equation. 3, 4, yes, and we have 3 equations. So Navier-Stokes is 3 equations. It's a vector equation. So 3, 4, 5. Then we have 3. Here is 8, and then we have this one, which is 9. And we have basically 8 unknowns. These are 8 unknowns. These are the 3 components of velocity, 3 components of magnetic field. We have temperature, and we have pressure. So the next step is that we reduce this to 6 unknowns and 6 equations. And to do this, we go from the true components of velocity and magnetic field to the toroidal decomposition. I mean, Uli briefly talked about it. So any flow field, or any field which is divergence-free, can be expressed in a field which has just the toroidal contributions, which is the first one, which has a double curl, and the toroidal contribution, which is the second one, which is just one curl. If you take the divergence of this obviously vanishes, because the divergence of any curl vanishes. So you can decompose the velocity field into 2 scalar potentials, the toroidal velocity scalar potential, toroidal velocity scalar potential. They are called W and Z in magic, and the same with the magnetic field, because the divergence of both vanishes. So G and H are the toroidal and toroidal potentials in the magnetic field. So now you have reduced basically the 6 unknowns, which are the 3 components of the flow and the 3 components of the magnetic field, into 4, which are these potentials. And by doing that, you have automatically fulfilled these 2 equations. So you don't have to solve them for them anymore. Okay. And what you have written down, actually now the components of the flow velocity you express in terms of toroidal and toroidal field contributions. And you can see that the toroidal field has no radial contribution. The only radial contribution comes from the toroidal field, and this has this horizontal Laplacian in front of it. We'll come back to that later. And then the horizontal components of the toroidal field, they depend on the radial derivative of the toroidal field. Important to remember. So, but the radial component is purely toroidal. And so this is the only magnetic field component that could potentially leave your dynamo check. Okay, so now we have reduced our unknowns to 6. The potentials, toroidal and toroidal, the temperature disturbance T prime around the background state, the pressure disturbance P prime around the background state. And so, and to solve for these 6 equations, 6 unknowns, we need 6 equations. And what we do is we actually construct a toroidal and toroidal Navier-Stokes equation. we just construct a colloidal and toroidal dynamo equation. We take the heat equation, because this was an equation for T prime, and we also need a pressure equation for P prime. So these 6 equations. So just a note here, other people take the curl of the Navier-Stokes equation and solve for that. So they actually solve what we call the vorticity equation, the advantage being that then the pressure being a gradient vanishes, so you don't have to solve for the pressure anymore. Right? Some people do that. The disadvantage is that you have an additional derivative, so you need possibly higher precision in your numerical methods. Right? So you save solving 1 out of 6 equations, but you need probably more grid points to do that. So now the question is, how do we get from the Navier-Stokes equation to a colloidal and to toroidal equation? So we need evolution equations for this. And this is rather simple. So if you, as I already said, I mean the radial, the velocity field, the radial component of the velocity field has just a colloidal contribution, no toroidal contribution. So if I take here just the radial component of the Navier-Stokes equation, I end up with just an evolution equation for the colloidal potential W. And to screen out an equation for the toroidal potential Z, I first take the curl, the Navier-Stokes equation. So in a sense, the vorticity equation of that, I take the radial component. And this then only has that in it. So there's only a contribution from the toroidal potential. So by these 2 operations, just taking the radial component and the radial component of the curl of the Navier-Stokes equation, I get 2 equations, which I then solve for the colloidal and toroidal potential. The same you can do with the magnetic field, because that is also decomposed in colloidal and toroidal parts. For the pressure equation, so we need an additional equation for the pressure. What we do is actually we take the horizontal divergence of the Navier-Stokes equation. That gives you an equation like this, which is an evolution equation for the radial derivative of the colloidal potential. This is not directly an equation for the evolution of the pressure, but we have 2 evolution equations, this one and this one, which involve the pressure. We have 2 equations, and you can solve this for W and for the pressure, though you don't have a direct evolution equation for the pressure. Numerically, you can do that. The pressure actually is a little bit problematic in the Boussinesq approximation. It has no, I would say, no direct physical meaning. It's a bit odd, but you can solve for it. And most people don't do that, as I say, because they take the curl. And if you do it, you can plot it, but it's a little bit difficult to interpret because of the Boussinesq approximation. Okay, well, so this actually tells you how we derive the equation, the colloidal and toroidal equations, by taking the radial components or the radial components of the curl, and then use the energy equation to solve for the T prime, or if you want the entropy prime, so the entropy disturbance, and also with this additional pressure equation. And now we have to talk about boundary conditions, because these are partial differential equations. We need boundary conditions. And for the flow, basically, as Uli said, there are 2 options. First of all, the radial flow always vanishes, because there's no flow into the boundaries. And the flow into the boundaries just has a radial component, and as I said, the radial component of the flow just depends on the colloidal potential. So when you set the colloidal potential to 0 at the boundaries, that means the radial component vanishes. So this is now the boundary condition you have to use to make the radial component vanish. It's a colloidal potential boundary condition. And for the horizontal flows, there are 2 choices. Either you say it's rigid, so horizontal flows are also 0, for example, right? Then that's why I've shown you this composition here. As you've seen, the colloidal horizontal flow components, horizontal, they depend on the radial derivative of W. So if you set this to 0 as a boundary condition, these 2 flow components will vanish. That's what we use. And then the toroidal flow is purely horizontal. So if you want these components to vanish, the horizontal flow components, you also have to that distance. So these are the three boundary conditions we use for these potentials in the case of rigid boundaries. Another choice is stress-free boundaries. So we say you can have a flow at the boundaries, along the boundaries, actually not into the boundaries, along, but this should exert no viscous stress on the boundaries. And you get this actually when you say that the radial derivative of the horizontal flow divided by the radius. If you look at the stress tensor, you can see that this is what you have to do, and this has to vanish. Well, and then it's a little bit complicated. You can also translate this into boundary conditions actually for the colloidal and toroidal potential, and they look like this. You'll also find this in your online manual, like everything I was saying here. So you can check whether these are the correct equations or not if you want. Okay, then additional equations, of course, for the temperature disturbance. Now, actually, I've left away the prime. So keep in mind when I talk about temperature now, it's always a temperature disturbance around the background state. But here we have a choice between actually three different ones, or actually, let's talk about the first of the two. You can fix the temperature to some given values that we think is appropriate, right? So, or say, basically we say the temperature is constant, and we can give it the value. Well, actually we can give it any value, because as I said, the temperature scale we choose is the difference between inner and outer boundary. That's a temperature scale. So if we say the outer boundary has the temperature 1 and the inner has the temperature 2, it should be higher, right? Then that would mean the temperature scale is 1. If I say the inner boundary has the temperature 100, the outer has the temperature 0, that would mean I just choose a different temperature scale, which would be 100 in this example. So just give this, you can just think of this, of giving it some values, and then you just redefine the temperature scale. Or actually what we do in the metric code, you don't have to think about it. If you use fixed temperatures on both boundaries, we always set the difference to 1. Okay, you just say, use this boundary condition, and you don't have to fix the actual temperature. Because it's just a way of rescaling, actually. The alternative is you fix the flux. And so the radial derivative. So K, the thermal conductivity times this radial derivative would be the heat flux. This is something we typically use for terrestrial planets, because, or for terrestrial planets, for example, or for Ganymede or whatever, because we have a rough idea what the heat flux out of the planet could be. So it's a good boundary condition. And we also know that basically if you have a mantle surrounding the dynamo region, that the mantle basically controls how much heat is allowed to escape the dynamo region. So it fixes this value. So in this case, it's a good idea to use this boundary condition. And what I noted as a third option is you can actually not say that the heat flux or the temperature is homogeneous at the bottom, but you can give it a pattern. So, for example, think about a planet where the sun shines on the planet. And typically, the equatorial region is hotter than the polar regions. So that may change the convection in the atmosphere. So you want to actually describe like the heat flux profile or the temperature profile or something like this. This you can do in Magic. And to describe that profile, you need spherical harmonics. We'll come to that later. Or typically for terrestrial planets, the mantle has some structure, and the structure translates into heat flux differences along the coromantle boundary. This is also something you can describe with the pattern you can describe in terms of spherical harmonics. Okay, now we come to the magnetic boundary conditions, and that's a bit more involved. And as Oli said, basically what we typically do is so actually no boundary conditions, these are matching conditions. So we know that the field outside of our dynamo region, assuming that this outside of the dynamo region has conductivity 0, that the currents have to vanish. So curl B equals current. So curl B equals 0. right, outside the dynamo region. And therefore, the magnetic field can be written as a potential field, where the potential field is now called E here. And so and we want to match to something like this. And now what we have to do is we want to match, well, we want to match all three components. So we know already that the toroidal magnetic field cannot leave our dynamo region because it has no radial component, so it has to vanish at the boundary to an insulator, right? So this is the boundary condition we have to use for the toroidal magnetic field potential. Now, for the colloidal field, you actually want to use, you match actually, well, first of all, the radial component of the field itself. In terms of the colloidal potential, it's this expression. I've shown that before. And here, that is just the radial derivative of that potential. And there's also minus sign here, so I dropped the minus sign from here. This is the matching condition for the radial component of the flow for the radial component to be continuous. And this is now the matching condition for the horizontal component. So remember, they depend on the radial derivative of G. Now, what you can do is, since you have these two conditions you have to fulfill, you can see that you actually can combine them so that VI drops out. Can you imagine that? There's two conditions to VI. If you know a little bit of VI, you know it's a potential solution, you can actually combine them in such a way that VI drops out. So, for example, you can take the horizontal divergence of this one, the radial derivatives of this equation, and then the right-hand sides are the same. And then you end up with a condition just for G. Right? This then, most people call this a boundary condition because it only involves just G. But actually, it's a matching condition. I prefer to call it that way. But you implement it like a boundary condition. So it just involves G. But it's only the case because you can eliminate the potential by combining these two conditions. So this combination is what we use in matching. Okay, this is already the equations. Well, the basic form, the colloidal toroidal equations. Say the recipe, how to derive them. I will show the equations we actually use tomorrow, the colloidal toroidal equations. But that's the essence of how we derive them from fundamental equations, from fundamental physical equations. Now, the next point would be to tell you a little bit about the code. How are we in time tomorrow? I think I have like half an hour, exactly. So this is something I did early this week. So I thought it's good to have a flow chart for matching. It's good to have a flow chart for matching. And then I looked up on the internet, how should you do this? And there's a DIN. In Germany, there's a DIN for everything. And it's called 6601. And that it tells you which kind of symbols you use for different parts of your code. So I just use the symbols. If you want, you can look up this DIN and check whether I was correct. So magic starts at some point. So this is an entry point part of your code. So you start your code. So this is supposed to be such a symbol. Right? The endpoint is the same symbol. Okay. And then, of course, you start with some input. Can you read this? Actually, it's a bit small, right? So let's talk about this way. So basically, we have three structures, driven, right? First, the ramp-up structure, where you read input and then you pre-compute something. You know, based on the input, there's a lot of fixed numbers and vectors that you use later on for your computation. So you only have to compute them once and for all, and then you reuse them in your time integration, right? So that's what I call the pre-computation. And then you go into your actual time-stepping model. So you solve a differential equation, you step them forward in time. So you go from one time step to the next, and this is basically, you go through here, and then you ask here, do I want a new time step, or do I think I'm finished? If you want a new time step, you go back up here, and you repeat that over. If you think you don't want a new time step, you go out here, so you write some output, you store your solution, and then you're done. So I call this final. So this is actually the workhorse. So this is where all the work is done. And I will mostly talk about this tomorrow. Today, we will concentrate on the render part, so on which input do we need and how do we get the input into Magic. And a little bit, we will talk about output as well. Okay, so let's talk about the first part. So first, we have to input the parameters, radian number, Ekman number, and so forth, right? But then parental number. And we do this by using a construct which is called named lists, and I'll show you an example in a minute. And something else we need, it's a time integration. So we need some initial field. And there are two options to use an initial field. Either you guess it, right? So you say, oh, easy guess, it's noise. Or you have a more intelligent guess. You say it's a field which has a threefold symmetry in us, or something else. So you have another initial guess. Or you say it's a diplomatic field, for example, right? So you can do that. What we typically do is we use a restart file. What we call as a restart file is the end product from a previous simulation. So you store all the fields, so velocity, magnetic field, temperature field, and pressure, plus some additional information you need for the restart, into a big file. These are called RST files. So restart, and then they have some additional tags. And these you can load for your next run. So and if your parameters didn't change too much from one run to the next, you know, it's a good idea to use that. So it's a good guess for your solution. And that solves you a lot of computational time. So if you don't start with a good guess for your solution, you have something that we call transient. So you integrate in time, but you start with a solution which is not truly a solution to your equations for the given parameters. So the numerics then leads a long time to adapt the final loop, end up something which is a sensible physical solution for the given parameters on resolution. So the closer you are, the shorter is this transient. So you save a lot of time, and it's particularly important if you have, high resolution problems where your transient can take you a month to get over on the big computer, right? And it's money to save, basically. Okay, and okay, so that's what I said. Either you have a restart part or you guess what your initial condition should be. Okay. And I think that we can briefly talk about what goes on in this part. Do we want to do that, or do we want our concept session? I think I skipped that out. We have more of it tomorrow. Well, what I could do is I point out a little bit the output. So we have different outputs. And normally what we do is we have our fields in Magic in a form where they are in horizontal spectral space. So they're given in terms of spherical harmonics. A spherical harmonic representation of your unknowns at a given radius are, so you have a spherical harmonic representation of degree L and order M. So, but sometimes we want output on a physical grid. If you want to display something, right? Your solution, you want to know what is it at any given point, and then you can make a nice 3D plot. And luckily, we have a transform in Magic, which does that anyway. Because what we do is, I talk about that tomorrow, we solve nonlinear terms on a physical grid. So once we have done that, so we have it present on the grid, so we dump the output here. And we dump it in two types of files, which are called G files or WOF files. So G stands for graphics. And you will actually work with visualization codes that use these G files. And in this G file, basically, all the fields are stored in single precision. The code runs in double precision. But if you want just a graphical visualization, single precision is certainly good enough because you cannot see the 5th digit or 6th or 7th digit anyway, right? So that's why we save space here by using single precision in the G file.
You can change it, actually.
Now you can change it. Okay. So if you want double precision in G-file, you can have it. Yeah. So historically, velocity field, magnetic field, and so the components now, not the potentials. We store the components. So the three components of the velocity field, the three components of the magnetic field, we store the temperature field. We don't store the pressure. Why not? Because, as I said, it's difficult to interpret anyway. People normally don't look at that. Maybe we find a reason that we want to look at that. Actually, I found a reason recently because I wanted to check some force balances, right? I mean, if you want to check force balances, you need the pressure because the pressure gradient is important part of it. So sometimes you want that, but for graphical visualization, it's not terribly helpful. That's why it's not stored in the G files. Well, and then we have something which we call MOV files. So MOV stands for movie. And what you typically want to do is with MOV files, you want to make a movie, so you store a lot of frames, right? And we don't want to do this for the whole information. Then this file would blow up, basically. So what you have to do is, if you want to use that, you have to predefine what is the quantity I want to look at, and at which cut through the solution. Or maybe you want to look at 3D. So you have to tell your code, for example, store the radial field at the outer boundary at these time frames. And then it does it. And the output files are called MOV files. And then you can use some software. We have IDL software, a MATLAB software, which actually can then create a movie there based on that. We will not talk about this during this workshop because that's a bit more involved. And yeah. And actually, the software we have is not so easy to handle. But yeah, maybe next workshop. Okay, so we will concentrate on the G files to make some simple graphic output at one snapshot in time, or at the end of your simulation. Right? So this is one output, and this is the output on the grid. Then we transform back to spherical harmonic representation, and that's a good point where you can basically calculate volume averages. So at this point, what we do is we calculate the total kinetic energy in the spherical shell, the total magnetic energy in the spherical shell, for example, and store this in output files that we also will analyze, well, maybe even today. Okay, and then, well, this is basically the end of the time step, and then we come to the final output, and this is now where we decide, okay, if you don't want a new time step, what we do is we will store a restart file that we can use for the next one. Actually, you can also do this for in-between steps. This is not correctly shown. You can also do this for in-between, should you decide to do that, just for safety reasons. I want to store a restart file because I don't know whether the computer will run 2 days stable. So you store in-between restart files. So if your computer crashes, you can use this file and continue the time integration based on that file. And then this is the stop then. And at the end, Magic will also write a lot of information, actually some diagnostic tools that will tell you how long the run lasted and what was the polarization used, how many cores did you use, and other diagnostic parameters. And that's all written in a file called log file. Okay, so again, input. So how does the input work? I've said it's on nameless, and just to remind you that you should go to the website, the Magic website, where something where this is explained. So you have input is organized in different namelets, lists, they have different names, and if you click on these, it will explain you exactly what are the different options. Now the good thing with name lists are that's a way in Fortran to use default values. So for every input parameter, there is a default value defined in Magic. And if you don't specify this parameter in the name list, it just uses the default. So this is the idea behind name list. So you don't have to specify all the different options you have if you don't need them or you want to default anyway. And to find that out, you can look into the online manual. So the first thing is you have to define the resolution of the grid you want to use. And this is done in the physical grid, not in the spectral, because that depends on each other. And I'll talk about that tomorrow. So for example, NR max is the number of radial grid points you use from inner to outer radius. And n-chat max is for the spectral representation in Chebyshev polynomials. I'll talk about this tomorrow. That needs to be later or smaller or the same as nr max. And n-phi tot is the resolution in azimuth, so once around the equator. So how many grid points do I want for that? And then you also have to specify if you have an inner core. And an inner core, there's no motion in the inner core, right? So the dynamo equation, there's no Navier-Stokes equation to be solved. And the dynamo equation is very simple because it can only be basically diffusion. So you have to solve a simplified dynamo equation in there. It's not, well, if the inner core rotates, for example, it's not just diffusion, but it's also the rotation. But this just changes the frame of reference. So this equation is very simple. But you have to specify the radial resolution for that, okay? And the horizontal resolution, so in phi and theta, is basically the same as used for the outer core. This is important. And then you have, well, basically Chebyshev representation for the inner core is this one. And then Mink is basically defines the azimuthal symmetry. So if Mink is 1, you basically resolve the full sphere. If you set Mink is 2, for example, you basically assume there's a 180-degree symmetry. So you only solve half of the sphere, and then you say the other half is just mirror symmetric with respect to the azimuth, right? And then, for example, if you say Mink is 4, then you just solve the quarter, and then you assume the given symmetry, right? So that's how you can solve computational time. You may ask the question, does it make sense? So is it a good representation of my solution? And indeed, there are some solutions where you know that they have this symmetry. So very close to onset of convection, for example, they have a given azimuthal symmetry. And you can use this then to use that symmetry right away, and you solve a lot of computational time. But that's only very close to onset, where everything is simple. If you crank up your radial numbers, you drive your system harder, everything becomes more complex. And then this typically uses applicability, but sometimes we use it nevertheless, because it saves computation. So we can say that if your system is very turbulent and your motion happens on very small scale, then it doesn't matter whether I have just 1/2 or 1/4, because the small scale of your convection is so small compared to the 1/4 that it doesn't matter. But that's an assumption, which helps to save computational time. And for many problems, it seems to be a good representation. But certainly only if your radial number is so large that the length scales are indeed small. So this was the first input name list, and basically, I didn't say that, but all these name lists are part of a file which is called input.nml for name list. Okay, they are all in there. And the name list, you always start this with an en passant, and then this is the name of the name list, and then you just specify the different parameters that you want to override, where you want to override the default, and then you end the name list with the slash. Okay. This is now the second important name list is the control name list, which basically controls your numerics. And the first part is what we call mode. So Magic can run in different modes. So the first one is mode 0, which is just a full self-consistent dynamo. So that's the full-fledged problem. The second one is mode 1. It's just convection, so we don't solve for the magnetic field. The third, 2, is a kinematic dynamo. We don't solve for the flow field, just for the magnetic field, but we need a flow field, right? But this is kept fixed. So we need a restart file that has a flow field in it, right? So, but then we keep it fixed, we don't update it. And then 3 is just for testing purposes, so we put a magnetic field, there's no flow, and we let it decay away. This is basically for testing purposes, because you have analytical solutions for the decay modes, right? Then 4 is magnetoconvection. That means basically you impose a magnetic field. And then this provides some Lorentz forces, and the flow evolves subject to Lorentz forces, right? Which are kept fixed in time. And then, well, another linear onset of convection is not so important. Then here it's something with that the full kinematic problem. In a way, we also update the flow, but there are no Lorentz forces. It's sometimes also interesting to do. And then these other options are for super rotating inner core, which is, we call it the spherical coax system. So you don't have convection. There are no temperature differences. There's no buoyancy. You drive the flows by differentially rotating in and out of boundary. So you rotate the inner boundary faster or slower than the other boundary. This causes flow instabilities, and they can also create a magnetic field. So these are the different options that we have here. So we won't talk about them more. So for this hands-on sessions, we will stick to mode 0. And the second is the tag. So this is the tag which is attached to all output files. So give this a unique name, and all the output files will have this tag, and you will be able to recognize which output files have been created by this particular route. And here you specify how many time steps you want to integrate. And these are two factors which concern the Coulomb-Friedrich-Levy criterion. Probably we won't talk about that much. So the time step is an adaptive time step, and it's adapted according to the flow velocity and the alphane velocity. And then if you make this factors larger, you're more critical. So basically you adapt more frequently, or you make your time step smaller even than you need it to resolve an effective flow velocity or an alphane velocity. So if that alpha is, for example, 10, then you say your time step is 10 times smaller or 20 times smaller, because there's already a factor, I think, than the alphane time scale you would need, basically. Right? So these are just safety factors, but you don't really have to change these normally, right? So that's the maximum time step you use. The time step is controlled by the Coulomb-Friedrich-Levy, but sometimes that's not good enough. And you know the time step should be smaller than what Coulomb-Friedrich-Levy tells you. Do you know what Coulomb-Friedrich-Levy means? Matti, do you know what Coulomb-Friedrich-Levy criterion means? No. So you have basically, let's say you have a numerical grid, right? And so say you have 2 grid points. And now you look at your flow velocity, and you look at the time scale you need to advect any quantities from one grid point to the next. That gives you a time, right? So the velocity to go from here to here, because the length is defined, and you then look at your velocity actually, and you know the time is basically this length d over velocity. Can you read that? I don't know. No, not so good. So and definitely know that your time step needs to be smaller. You will have to resolve this effective time step, right? And that's basically formulated by the Coulomb-Friedrich-Levy criterion. Now, if you have a magnetic field, you also have magnetic disturbances can travel without motion along field lines. And that's given by the alphane velocity. So they can also travel. So you have a way of traveling information, magnetic field, from one grid point to the next in a given time, which is then defined not by the float velocity, but by the alphane velocity, which scales with magnetic field strength, actually. So you can modify Coulomb-Friedrich-Levy to also take that into account. So you can calculate this velocity, right? And then you know your time step should also be smaller than this. But by how much smaller it's actually taken, this is defined by the Coulomb factor, which is the Coulomb factor, which depends on the flow speed, u, right? And alpha, which depends on the alphane velocity, so the magnetic wave velocity, so to say. Okay, but sometimes, as I say, this is not good enough. So you have waves in your system which travel fast, very fast. So, for example, with the rotation time scale, These are called inertial waves. And they can be faster than your advection or your Alfvén velocity. And therefore, you can also choose a dt max. So you know your time step will never be smaller than that. Right? So if you look at your solution and you see there is something strange going on, sometimes it's good to make that smaller. There are different safety measures built into metric, which actually make this already quite small. But sometimes you have to adjust this as well. But I think for this workshop, you don't have to touch that. Then I think this is not so interesting. This tells you, but that I check these criteria each 5th time step. Okay, not every time step. That's not this. Okay, then there is a weight here, which is not interesting. I'll talk about this a bit tomorrow. And then you can actually specify the runtime. I want Magic to run for 12 hours, 0 minutes, and then it shuts down. And it writes a restart file, it finishes off as it should, right? Okay. So this now is the third control, nameless, which is important. And here you specify actually the parameters: Rayleigh number, Ekman number, Prandtl number, magnetic Prandtl number. The aspect ratio is called Rudd ratio. And then here you specify the boundary conditions I have been talking about. The top always means outer radius, bot means bottom radius, and it's always called K because it's an integer. And then this refers to entropy or temperature. This refers to velocity. This refers to magnetic field. And then, well, there's just different options you control by changing these integers. For example, K tops 1 means fixed entropy or fixed temperature at the outer boundary. K tops 2 means fixed entropy flux or fixed temperature flux, heat flux at the outer boundary. So this is actually now copied from the online manual. There you can check all this. Or K top B means either stress free is 1 at the outer boundary, and or 2 is rigid boundary condition at the outer boundary. Okay, now I also said we need a start field, a restart field. There are 2 ways, as I said, to define that. One is you read a restart file. So what you have to say is you have to say L_start_file. That's L stands for logical equals true. Here it's false in this example. This is the next example you will use. You have to say it's true, and then here you have to put the name of the restart file. Okay? Or alternatively, you can guess your initial solution, right? And since we will run a very simple case, first we know what that should be. So that's an easier way to do here. So you start from actually a dipole field, post magnetic dipole field. B stands for magnetic field potential, right? So you impose that, and 3 means dipole field. This is the amplitude of the field. And then you also impose a temperature or entropy disturbance, and this has means 4-fold symmetry, but you can also read that in the online video. That's a way of imposing a certain symmetry, degree, and order 4 actually. And then the amplitude is 0.1, but it doesn't really matter much which amplitude you use here. Okay, that's for the input, and then output. As I say, we have this log file. This log file keeps track of your run actually. It starts with giving you the version you have been using for Magic, and then basically all input parameters are written in that log file. Also the ones which have been defined by default via the nameless. So if you look at the log file, you exactly know which is the condition we're running. And then it also gives information about the parallelization, the runtime, and so forth and so forth. It also writes some important output variables at the end, so time average energy and something like that. You can look at that. And it also tells you when it has changed the time step, because the wrong criterion was violated. And it also tells you when important output files were written. So G files, MOV files, something like that. So basically, all you need to know about your run is contained in this log file. So, and then there are, of course, additional, well, how do you control the log file? Basically, there's one important parameter, well, there are different ways to control it. We will tell you about one, basically, n log step. It tells you at each Well, at each long and log step, I want this output. If you set this to 1, every time step you write output. So that also means that every time step you write, for example, the kinetic energy, calculate the total kinetic energy, and write this into the respective output file. Same for the magnetic energy, for other quantities. So this is when actually all these important quantities are computed and stored in respective output files. Do you want this to be 1? Normally, no. Right? If you do this, you drive your computer center crazy. Because you write to the disk all the time. A lot of information. You don't want that. And you only have to write it when something changes significantly. So the typical timescales, we expect changes, right? So typically, you would set that to at least 100 or 1,000. Right? So the typical timescale for variation in energy is magnetic energy, kinetic energy. Today we will use 1 because we don't write much output. Anyway, it's a simple case, and you want to see the evolution. Therefore, Ankit has chosen 1 here. Now, the graphic files, I've told you, you write graphic files that you can use for visualization. Here you just give the number of graphic files you want to store. So if you, for example, have told your run to run 10,000 time steps, and you say n graphs is 10, then you will have each 1,000 time steps 1 G file. If you set it to 1, you will have just 1 at the end. Same for restart files, right? So normally it's set to 1, store this 1 at the end. If you think your computing system is not very stable, store in between files. Okay, this is an additional ID, which is not important. This is just used for the graphics output. So if you have graphic files, this is a character in that. So if you want to have automatical labeling of your graphic files, you can use that. Okay, and then for movie, we don't use that here. As other output we don't use here. So this is the input. I told you now about the input. Now let's briefly look at the output, and the online manual, of course, is very helpful in this. So this is now kinetic energy. That's generally called E_keen for kinetic energy, and then at the end is the tag you gave in the input name list, perspective control input name list. And then this is just the way it's computed, or it's the definition, of course. It's the volume integrated momentum, right? And the kinetic energy, you need the 1/2, additional 1/2. And this has a colloidal and toroidal part based on the colloidal flow and the toroidal flow, and we store both separately. And here is just, this tells you, what is in each column of that output files. First column, of course, is time, and then second is colloidal energies, third toroidal energy, and then we just have the axisymmetric parts, and then we have the equatorial-symmetric parts, and so forth. So there are some symmetries are checked there as well. So that's a file we will be looking at. And yeah, I already said this. There are additional files, G files, generally called G_, and then there's a number depending on how many files you want, 1, 2, 3, 4, 5. And then at the end, you can also store a time averaged field. So you have averaged over magnetic field or over flow field, and you want to know what is my time averaged. That is also stored if you specify that. In the movie files, I already said this is some star, so that depends now if you want to have the radiomagnetic field at the outer boundary field. It's called BR_CMB_MOV.tag, and the restart file is always called like that. Okay, and that brings me to the end of my talk. So just a conclusion, Magic in the moment I think is the most efficient code out there, at least if you have used less than say 2,000 cores or so. It's publicly available on GitHub, and it has a nice documentation, and I think you should be able to do your first runs. And now you are basically our test person. You will test whether the documentation we have online is good enough to make you run the code. And with this, I hand over to Ankit and Thomas, because they are supposed to run this first hands-on session. And for this, you will have to log into your screens, or you can switched on already. But so So the screens should all be on, and you are all logged in already as the user you're supposed to be. So we have just simple names. So the users are called Magic 01 to Magic 16. Magic 1 is over here. Marcus should be Magic 02, and then 3, 4, 5, 6, 7, and so forth. And right at the back is Magic Florian. You're Magic 16. You should be Magic 16. And if you need a password, you're not already logged in. This is the password. It's called workshop, capital W, and then the O's are replaced with zeros, and there is an exclamation mark at the end. And yeah, it's basically, and so it's organized like this, that everybody of you, so we have an in-house cluster. This is an AMD cluster, Dell AMD cluster. So each node has 48 cores. And each group of 2 people, or in Marcus' case, it's just 1, has 24 cores available. These 48. They are reserved to you, providing you run them in the correct way, and Ankit and Tamal will tell you now how.
Okay. Okay. Well, I guess the login now you got it. So maybe first I wait that I logged on the same client correctly.
So F8,
yeah.
So if it's sleeping, press F8. And then there's a small menu, and then you have to press send F8. So then it sends to the mainframe, and then you should be able to access your screen.
Okay, so and then you have to unclip it. It's not working yet. Were you here? Okay. So then you should use the SSH command to log on the computational node. So you should follow SSH -y, no username, arrow, and then this corresponding atlas node. So and the atlas node corresponds this way, so that the magic 1 and 2 goes to atlas 1, 3, 4 to 2, and to 8 here. That's in the code. Here.
Yeah, but it's not what it does.
It's not proper. Okay, so so yeah, it's not 0 here. It's 0 here. Sorry, yeah. Workshop is W0RKSH0P.
No, but we need to start first. The start.
The R bus, the edge.
And the number is plus.
So does it work? Did you manage to connect on the site?
Trying to get it run on my laptop.
Ah,
And
okay.
it didn't compile, but I get a strange error message.
Yeah.
About the level.
Did you manage to SSH connection?
No, we can do that.
Yeah, that's
Okay.
You want to sit here?
Yes, I did the CMake directory. You have make sure that you don't use open. No, it's working, but on your laptop you need a few Ideally it will work, but I guess you use OpenMPI.
Yeah, something like that.
So you have to export an environment variable such that thread safety level to multiple. That is not supported in OpenMPI. It's supported in OpenMPI CH.
I don't know which version I have. It might be that I have MPI.
You can see OpenMPI. Otherwise there will be another one.
Tell them that we are looking Okay, yeah, sure. Yeah. So I can go one step. So the next step is that you clone the code. So
which is not supported by OpenMPI.
So well, just use Git and then clone it from the repository online.
Only OpenMPI without MPI.
No. But you can use pure MPI. OpenMPI only disregards the MPI. Just for the main parallelization is the radial direction. So I now do the CMake. And you do say CMake minus K. No.
Correctly.
But you did it already.
So copy pasting from the manual.
Oh, yeah.
Yeah, you're right. That was the right thing.
Minus G does parallel.
Yeah, I think there was some bug introduced from last day. So yeah, it seems that there is some bugs. Yeah, it's a bug. Yeah, no, it's a bug that we use the MKL for bugs. No, for the did you use the mask and the library? Or it might be down. I think I introduced the bug. Can't figure out where it comes from. So yeah, but it should be fine here. So did everybody manage to clone the code? Oh yeah.
And this is actually part of the other test. So the reference should be numerical.
How can I visualize it? Parallel?
Yes. Also, we have a Python suite available. You see the directory Python. First time. So, what you do first is you source. Yes.
I don't know. I think that's
And you are on which node?
But we can install it. Yeah. But so it adds it to the Python stuff, and then when you load You don't have MATLAB. MATLAB. Sci-fi.
It seems to get a bit better.
The visualization, yeah, based on Python. And we also have a Python module for which takes this graphic first, converts it into pictures first, which you can use to view by comparison. Yeah, we'll show that as well.
Okay, then I'll wait.
Yeah.
Right, thanks. Oh, ich muss endlich mal Python lernen. Das bin ich auch schon die ganze Zeit.
Aber Python ist bestimmt auch relativ schnell.
Ja, es ist genau so. Deswegen, ja, genau.
Oder würde ich dann die Empfehlung Skype weil das viel schon vorkommt, geteilt.
Die andere macht eigentlich C-Make, das sind Informationen.
So it sounds like most of you compile the code now, so we can go to the next step. So you're going to create a directory and run the benchmark that we presented this morning. So I suggest you create it in your home directory like that. Then you just go to this directory and copy the executable you just compiled. And as Johannes presented just before, you need an input name list, which should be in your home directory. Ja.
Objektorientiert programmieren.
Where's the
No, you don't need to copy anything. Ah, yeah, you need to go into one there. Yeah, so don't copy that.
Weißt du, wie es geht? Kompiliert haben wir
Here is the point towards the CV. Because if you move it, then this one is pointing toward the source, so it's going to be. Okay, so I suppose now. So did most of you manage to create this directory here and copy the name list? So I just go briefly through what's actually in the name list, although I can go quick because Johannes went through it already. So the first.
Was die Nameless, die gibt es in diesen Benchmark. Okay.
Okay. So let's go back. So the first part of the name list just describes the resolution you're going to use here. So the number of radial grid points, the number of azimuthal grid points, and the possible azimuthal symmetry as Johannes described. So no need to spend too much time here. Well, the control name list just tells you that you're going to run 40,000 time step, which should be roughly an hour of run if you use the 8 CPUs here. So, well, then the physical parameters section describes the dimensionless numbers that are going to be used during this run. So it's a Rayleigh number of 1.1 10 to 5, and an Ekman number of 10 to -3. So it corresponds to the Dynamo benchmark that we showed you this morning. So it's a very simple solution, pretty large scale, which is supposed to sustain a large scale dipolar magnetic field. Okay, and here are the different magnetic and mechanical boundary condition and entropy boundary condition that Johannes described just before. So the fourth part of the name list contains the start field situation. So in case you want to continue your run, you would put here L start field equal true, and then give the name of the final restart file that Magic produced during the run. But here you want to initiate it from 0. So you put it to false, and then you put an initial magnetic field, which is a dipole here. So 3 corresponds to the dipole. You put an initial amplitude of 1, so which means that you initiate your system with a strong initial magnetic field of less than a number of unity. And then in addition to that, you put some initial entropy perturbation. So you can wonder why I put 0.404 here. So it means that I impose at the very beginning perturbation of spherical harmonic degree L equals 4 and spherical harmonic degree order M equals 4, 2. So why did I do that? Because I know in advance that the final solution will have a strong 4-fold symmetry in azimuth. So to speed up a little bit the computation, I decided to put that in at the very beginning, because such that you can convert your solution within the next hour or so. But in general, I would say for any other setup than this one, you might want to put random noise or something here instead of just a specific spherical harmonic degree and order. Okay, then it's just the output. So the code is gonna write some outputs every 50 time steps. It's gonna write kinetic energy, magnetic energy, and so forth and so on every 50 time steps, thanks to the first line of the name list we specified here. It's going to produce 3 graphic files, so 3 files which contain the whole 3D field of velocity, magnetic field, and entropy during the run. And it's going to produce 1 spectra as well, one magnetic and kinetic energy spectra at the end of the run. And that's it. And here, well, it's just conducting in your core, and that's about it. Okay, so now to run. So you have to export this first variable, and this is mainly because here you are directly running on some nodes, so you have to be careful that as you are sharing some nodes, you are not degrading the performance. So you have to export this variable here as a first step, and make sure really you export it correctly. Otherwise, well, you may just share your CPUs with the neighbor instead of you using 100% of one CPU. So the plan is that you run this benchmark with 8 CPUs. So you export this variable equal to 8, because in the second step, you're going to run with 8 CPUs here. So, well, be careful with the syntax here, because if you make a typo here, it won't complain or do anything, right? But, well, you're just going to run with degraded performance, or maybe you're going to degrade the performance of your neighbor. You don't know. So try to make sure that you type it correctly. Sorry for that. I mean, in general, on a production cluster, you don't need that, right? It's just here because you are interactively running on some nodes. You have to make sure that you are really correctly sharing the available power, potential power. Yes, then you can run. So once it's done, you just use the MPI exec command, and you specify -n, which gives the number of CPUs. You put 8 CPUs, use your executable, and you put name list. And that's it. Yeah. but you probably copied it. Well,
Das Weihnachten da jetzt genommen. Based on
Na, dann wahrscheinlich das, was runtergeladen wurde.
Wow.
Also das ist einfach aus Finger, was mir halt geklont vom
ja, eine gute Platte da bei dir.
Deswegen so, also das Login hast du ja auch.
Ja, habe ich schon runtergeladen.
Genau, einfach so. Kannst du schon die Directory machen und dann in der Directory machst als Git-Clone und den URL.
Genau, und wo ist dann das Namesfile reingebaut? Bei Samples gibt es ganz viele. Ja, das war so schnell.
Die läuft sich auch gerade.
So in the future, if you want to
I just so it's running back to
Es gibt ja mehrere Bands.
yeah, so yeah.
For some reason, I want that.
Okay. Well, I have
In der Ordnung sind wir.
Achso, okay, dann mach mal deinen Dynamo.
Alles hat gerade gut an der Dynamo Band sein.
Einfach den Input nehmen natürlich, ne?
Ja, ja. Überall anders. Es war kein anderes.
Achso, auch die Werte waren anders, hast du mal geguckt, ja. No way, actually call it
Dynamo
Dynamo.
yeah, samples, but then you
Dynamo.
So it's not
ja, eigentlich rechnest du da auch die, ja. Aber ihr habt ja dann mal den Core gezählt, oder? Ja. Hast du aber auch bei dir nee. Ach, ihr habt ja unten das gemacht, oder rechts, oder?
große Arbeitsschatz.
Auf den Maschinen.
Aber jetzt sprechen wir quasi die Zusammenarbeit, aber nur einzeln, ja.
Das ist einer. Die haben alle 32.
Ach so.
Aber das ist ja das einzige Inhouse.
Ansonsten haben wir noch so eine Spray-Hersteller. Zu Bier. Wir haben mehr. Weil das ist kein Fall. Nichts nur 2000 Pro.
Also auch nicht mehr auf der mal dokumentiert oder was da mal gekommen.
Die haben mir mal gekommen, weil das und ist nur seid ihr bereit? Jetzt geht's los. Ein halbes Jahr Verzögerung, Ausfälle, Technik. Und wir haben mal das Test. Herstellen.
Okay.
Also
Der ist halt immer noch
eigentlich
das ist ja mal gegen DDR.
Ich kann halt ja, das ist der NASA.
Ja,
Ina muss immer goldene Nadel. Das ist nicht gesehen.
ja.
Der goldene Nagel. Das ist ich musste da nicht Stück.
Das war einfach nur Brief, oder?
Ja, wir müssen immer was erzählen. Schöne Videos zeigen.
Ja, dafür kann man quasi, ja, ja, klar. Ja, sehr komfortabel.
Ich muss gar nicht so viel sein. 512 Kerne.
Aber der war ja immer der Teil, dass es teuer war.
Das ist dann teuer und dann haben sie auch festgestellt, die Infrastrukturzentrale doch so wunderbar
So, echt?
Die sagen uns doch mal, ja, wir Stromverbrauch, wir wollen, wir zahlen das alles, kein Problem, aber dann doch wieder,
Aber die Eltern alle antworten. Aber das machen sie nur. Also, ja, ganz viel Klimaforschung. Das ist eigentlich auch so ein Thema. Wechsel der Schale einerseits komplett ausgelassen, im Winter aber wir machen Klimaforschung. Wechsel aus. Ja, war schon
zwangsweise.
dann mit
Vielleicht ist da auch Klimaerwärmung mehr.
oder die Wanderstück auf alles.
Ja, gut, aber so ein Pflaster, ich meine, das muss ja immer laufen lassen, was soll das? Das ist ja auch muss es eigentlich immer benutzen. Ich meine, ich mache das nicht 1000 oder 500 gerne, wenn ich dann sage, 24 Stunden brav.
Ja, im Endeffekt könnte das DDR sagen, zu Nachtzeiten, wenn es Stunden sind oder dazu aussteigen und die Auslandssendung, das könnte die tollen Sachen drüber laufen lassen.
Aber gerade nachts lässt du doch auch rechnen.
Du kannst nicht. Ich habe mal gesagt, der hat letztens zu Hause eine Zielservice zu sein, die freigegeben und hat damit richtig gutes Geld verdient. Und dann hat er noch mit der Abwerbung von der Service zu sein ausgeheizt. Also irgendwie 20.000 Euro investiert und meinte aber, das ist schon auch schon genug. Ich weiß auch nicht, wie ich das mache. Also ich habe mich damit nicht weiter beschäftigt. Das geht jetzt wieder. Da brauchst du Spezialaktivitäten. Monat anlassen, dann haben wir vielleicht 10. Ja, das ist die 1000 Euro Strom. So, jetzt geht ja alles eingerichtet. Das waren noch nicht so viele Zeitschritte, die ich hier mache.
Ja, und die schauen dann.
Jetzt sind das ja eingestellt, das ist mal so genau. Weißt du noch, was das ja, es war bei uns die größte Zeit. Endtimes hier.
Ja.
50.
Was ist
40.000.
was bei Samples ist, wo sie Netz also das ist ein Sample von einem Dynamo.
Ja.
Ja.
Würde man 4.000. Das ist ja wahrscheinlich wieder gestorben. So. So, ja, also kannst du ja auch mal anschauen.
Nee, ach so, das erste. Nee, ich habe es aber ich weiß nicht.
Yeah, we'll end on the topic.
Input bench. Bench, Input bench. Input bench.
Gibt's hier wahrscheinlich gar nicht. Vielleicht speziell auf den Cluster hinterlegen.
Nee, wir haben ja so ein Contrary auch einfach gezogen.
Ja, aber es gibt gar kein Benchmark-Verzeichnis. Sample.
Ja.
Welches Benchmark machst du denn?
Ja, was ich uns gesagt habe.
Das liegt bei mir durch.
Wieso Startfeld ist bei dir da auch?
Startfeld. L-Startfeld wird ja auch gesetzt.
Hast du das komplette Verzeichnis reinkopiert? Wahrscheinlich, ne?
Ja. Originalverzeichnis.
Do you have to buy libraries?
Super.
Du kannst natürlich auch du kannst es ändern.
Aber du brauchst ja dann auch den.
Oh yeah, because it tries to read the file, I think.
It tries to read the file.
So it's trying to read the file.
Nee, das ist schon designt.
Mehr Zeit.
Ach so, okay.
Okay, but very well. I think we can continue after the break, but yeah, for those of you who want to look at the data, you can already. Well, there is a Python toolkit provided with Magic, so it should be able to help you to display some Magic queries. So.
Methode drin?
Wir haben dieses Ihnen, hast du das in deinem Dynamos drin?
Wie das ist. Weil das ist sowieso egal. Und der nimmt einen Restart.
Ach so, wir hatten keine Restart, wir hatten Laufbord.
Hattet ihr L-Star-Zeit?
Nee, Tor.
Ah, setz mal.
Aber ich meine, das ist schon die Runde.
Nee, dann brauchst du nicht.
Dann brauchst du auch nicht so viele Zeitschritte wahrscheinlich.
Ja gut, ja, wir haben hier trotzdem 40.000.
Nee, ich glaube, ja. Also, weiß man jetzt nicht, ob man das nochmal anguckt.
Ja, aber er macht ja 3 Grafikauslagen.
Ja, aber er geht wahrscheinlich nicht auf 40.000 Schritte, wenn er jetzt 40.000 ist ja nur der maximale Anteil. Also nach 40.000 bis 8 nur bei Schauer, also wäre das wahrscheinlich
Magic.
Deswegen wird es da oben gehen.
Ich kann auch mal diese
Ja.
Ja, aber ich kann nicht.
Nee,
Ja, das ist ja jetzt.
Nee, ich hatte das jetzt einfach mal gemacht. Also ich meine, ich weiß aber nicht, ob das jetzt so ist.
Ja.
Oh, no bugs. Everything's working.
So you're running on your laptop?
Yeah.
you did this. Ankit says there is a routine to convert the graphic files.
Oh yeah, it's the next slide. But first you have to try whether you can load it properly and things like that.
Yeah, but I'm now on the Magic app, so I guess I have to change it to.
If you source the source me correctly, it should be fine. So
Seriously? In the Git.
or maybe one step that you need to pay attention of this step with the source me sh. It's pretty important for the post-processing because it's setting up some environment variable. So if you skip this step, it might not work in the rest of the thing here. So make sure that you source it. Otherwise, the stuff displayed here won't work.
We entered the source .sh thing, but for some reason once out of home for some time, we say from that report, then it doesn't say it doesn't know that.
Okay, yeah, that's very fine.
At least.
Good. So it's working. So that will try to read.
So what you have here is downtime evolution of the kinetic energy. And you have the colloidal and toroidal quantities. So in red, steroidal, in blue, colloidal, and black. And then you have the axisymmetric right here in black. So yeah, what you see is that while you have the transient phase at the beginning, and it grows, come back to growth, and then you see it separate. So it's supposed to be settled already. OC, which is the core, and you see that your magnetic field has a dynamo here, maintaining magnetic over time. That the colloidal field is very strong, stronger than the toroidal here. And also interestingly, the axisymmetric distribution is pretty dash time corresponds to a large fraction of the total. So it tells you that you're going to have your magnetic field very axisymmetric, so dipole.
The surface of the type. No,
Is it so? Well, once you reach 100%, should be fairly.
And just because of the story, it just didn't remember it because we did it at the beginning.
You probably did it on the other,
Or
the other one. Yeah.
Okay.
So you have to do it on each session.
Okay, yeah, each terminal. Oh, yeah.
Yes. Otherwise, if you,
Yeah,
if you,
sure.
if you don't want to do it each time, you just edit.
Okay.
Which MPI are you using? Yeah, there's a common the common so the data type that we use for the graphics
Okay.
to like now supported by
Do I have to change into the directory?
So what can you do? Nothing.
No,
So-
you have to use API.
You could.
Okay. API
Samples
Where did you run?
in this here.
Okay. You have the data. You have some data here.
I think so.
The data here is good. What is the format?
So now
No,
This?
that's binary.
Yes. From Magic Import Star. Let's probably open API can Yes.
let's
So
try the surface.
we use an
Already
API
familiar.
statement. The data type is specified.
But do you have a
for
G file?
external that you
Yeah, you have one.
use,
So IVA won't one won't work.
API output
Well, I didn't explain it yet, but
it can be
won't work because you don't have a G underscore one. You don't have a G underscore
Yeah.
ADE.
So we use the
So I mean, you didn't take the name list I provided, but you just take your own.
Okay.
That's why before the workshop, we upgrade the FACH version on the cluster.
There you go.
Oh, sorry.
No, because you didn't take the name list I provided. So the one that is
Yeah.
provided
Maybe
there
try it with FACH.
is running smaller.
It doesn't
One is
even
just
run
running
with that, then we
time
can-
test. So it's very short and it doesn't produce the files which are supposed to be produced by the name list.
Just say
Provided there. But that's all right. I mean, have a look at this. That's fine.
Okay, cool. Thanks.
Did you run it with MPI or?
Yeah.
Yeah. What fun.
Yeah.
Good work. Okay, good.
So I think
Okay.
there's the opening pay box.
One, not two, then this one.
Yeah, FACH.
Are you running on your lab? Okay. Well, I mean, you can make it work with exporting the FQF and the end. But yeah.
Oh, yeah. That should work.
But I mean, but it's gonna be easier with MPICH though.
So
What is it? What you were saying?
So what did you say, Magic?
Yeah. Magic.
But did you source the thing?
Yeah, this was me.
Yeah.
Maybe it's okay. This is only this happening. I didn't source it in this terminal. Only in the first one. Yeah, in the first one it's there. Okay, so maybe go to the first one. I'll try to show you an example. If this works. Okay, so did any one of you reach this stage where you can start playing with the visualization? Guys still running, but
Was eigentlich alles auch.
Come on.
whatever.
People.
Das war auch mit oben, wenn du einkompilieren.
Ohne. Sowieso. Das ist eigentlich wurscht.
Ah. Because the IOR is the number of the file produced. So if you have two graphic files, G underscore 1, G underscore 2. So here it's trying to read something named G underscore 1, which is not there. Just whatever you want to see.
Das war mit einer MPI.
Was brauchst du?
IDR is ready.
Was gibt es noch? Das hat er ja auch gesagt, so irgendwie Anaconda oder Skype.
Nein, das Ding heißt nur so eben. Das heißt,
Achso, ja, nee.
also du kommst eigentlich mit dem Ubuntu, kommst du zurecht. Alles in
Das ist alles.
genau, du kannst also nur das installiert man das
Ja, bloß ich glaube, auf meinem Rechner, den ich jetzt hier nicht habe, das wollte ich machen. Wieder bei dran. Aber ich habe auch kaum noch internen Speicher. Ich habe nur noch 4 Gigabyte. Der hat auch nur so 40 Gigabyte.
Did you change something now that it's to make it? Maybe I restart.
Okay, just a couple of details. I mean, what is this guy actually doing here? So, so it's loading the file which is named e_kin dot your extension, which should be test for the run you did here. And this file is just an ASCII file where the first column is the time, the second column is the poloidal kinetic energy, the third column is the toroidal kinetic energy, then you have the axisymmetric poloidal, the axisymmetric toroidal, and so forth and so on. So what it does here is that it's plotting it, but you can also access the data through TS. So TS is an object here. So if you type like TS dot and then tab, it's going to give you a lot of things that you can use. So maybe I can show it to you.
You're using GTK backend.
Yeah.
Yeah. Okay. Okay. It's very convenient.
Let's go.
Okay, shit.
So for instance, if I do, you know, time is an array and it contains all the data. So the time series, and then if I do in fall, it contains the value that have been read in the file. So which means that if you want further on to manipulate the data, you can use the TS object to just access anything which is read in the file. It also contains like the control parameters, like Rayleigh number. Oh, sorry. So, or you know, Ekman number. EK. So if you use tab, it usually give the completion possible options. So you are just doing ts.ek and then tab, and then it just leaves me the possible content of the whole thing, right? So then you see that Ekman is there, things like that. So it allows you to display and then manipulate the data. You can even completely turn off the display by just doing that. If you want just to manipulate, just put the iPad to false, and then it just loads without plotting. Well, it's just useful if you want to do some additional analysis on the outputs, like I don't know, averaging over time or doing some stuff like that. Right. Okay, and the surf. Well, the surf, I don't know if all of you reached this stage already, so yeah, wait.
Ah no, Magic, CD Magic. Aber wir müssen ja doch nicht.
So the problem was here. So this controls the pricing. The GTK is installed and our source media text set back in the GTK. But for some reason it doesn't properly work. So this one works for the GTK. Because it's a pure Python. It doesn't work.
Yes.
Increase the control level to so the benchmark step is supposed to be 4-4 symmetry. So if you look at
Ja, vielleicht so sich das dann aus den unterschiedlichen Versionen.
positive
So if you each time you log in, yeah, which is what it does. Yeah, I should be reaching. Well, I don't have the data on my PC, so I cannot show the G file. So I'll make your own here, so I can enter that. But that's okay. I have the benchmark, just a saturated benchmark, so I can just explain everything. So for those of you who were not here when I explained, so when you do that, so well, the command that was displayed was without that. So when you do that, it's just reading the ASCII file, which is named e_kin.test, which is the file which you should have produced during the run. And this file is just an ASCII table. The first column is the time. And the second column is the poloidal kinetic energy. The third column is toroidal kinetic energy. Fourth column is axisymmetric poloidal. Fourth column is axisymmetric toroidal, and so forth and so on. So when you do that, it's just reading this file. And so it's basically displaying, well, what most of you have seen. So the time evolution of these different quantities as just mentioned. Yeah.
Can you choose the font size?
Oh, yeah, sure. I can make it bigger. Well, okay, that's not very good. Come on. Ah, so I wanted to do it this way. Well, so what's the
You go to preferences and there should be.
Click somewhere else, probably. No. Well, sorry, I can't find that there.
Okay. Yeah, edit your profile.
Ah, here.
Yeah.
So, oh yeah. There we go. Is that enough? Or, I think that's enough, right? Or can you even bigger? Okay. Well, I changed the whole thing.
I go to 20.
Okay. It's not so easy actually.
You extended your screen. Yeah, that looks
So when you do that, it's just supposed to plot something here. I cannot really show you on my laptop because I don't have the data here. But well, you will see the time evolution of the kinetic energy. So the black line is the total kinetic energy, and then the blue line is the poloidal part, the red line is the toroidal part. So the sum of the blue plus the red is the total black line. And then you have the axisymmetric fraction of those, which are displayed as dashed lines. Is that clear for all of you? Okay, and the interesting thing is that it's not only loading here, it's just also storing the data. It's just storing the data in an object here, which is named TS. So if you type TS.time, it gives you an array which contains all your time, right? And if you do ts.ekin total, for instance, this is the total kinetic energy. So let's say I want to back up my own figure here. Well, you just do a plot, you know, ts.time, ts.ekin. And then the figure appears somewhere, but obviously, well, here. But obviously, I mean, in that case, I already reached the saturation of your simulation, so I just have the final plot of the rest. It's not very interesting, but just to tell you that you can just back up your own figures because the TS here contains everything in principle. So, and it also contains all the control parameters that you set at the very beginning. So if you want to get your Rayleigh number, you have it there, right? TS that RA, it gives you this value, which is precisely the Rayleigh number you had at the beginning. Or PR, you know, you can have PR if you want the Prandtl number, or PR mag if you want the magnetic Prandtl number. And so forth. Okay. So that's basically how you can manipulate your data. So the same thing happens when you want to change the output. So Magic TS can basically load all the time series that have been produced. So sorry, I don't have. Yes. So let's plot it. So I don't know if I want to plot the magnetic energy versus not. Okay. Well, it's here. But again, my simulation is over, so I have just the last. I mean, I'm not running the same thing as you here. It's just the final part of the time series, so you should have something with the nice transient in the final state. So again, this is the magnetic energy. Black is total, blue is poloidal, red is toroidal, and then the dashed line is always the fraction which is axisymmetric. So in the solution that you just run, what you see right away is, like, if you look at the magnetic poloidal, so the blue line, you have a large fraction which is axisymmetric. So it tells you that already your magnetic field is going to have a large axisymmetric fraction, so meaning that it's very likely dominated by a dipole. So a way to check that, we can already check that with the additional diagnostic that have been produced in the PAR file. So the PAR file, you just do that. Okay, so the PAR file contains two panels, or plots two things. So the PAR file contains some important diagnostics that Uli and Johannes discussed. So the first one contains, for instance, the time evolution of the magnetic Reynolds number, the Elsasser number, the Rossby number. So all these quantities that are key diagnostic quantities that come out when you run the dynamo model. So for instance, as Uli mentioned, you can look at the magnetic Reynolds number while it's going upscale here. So maybe go look here for the time being. Well, you see that the magnetic Reynolds number is around 45, so it's very, very close to the minimum magnetic Reynolds number you would need to have dynamo action at all. And well, and the second panel here is the evolution of the dipolarity. So how dipolar is your field versus time? And here it just confirms what I said before. So if you look at the green line here, this is the dipolarity of the magnetic field at the surface, at the CMB if you want. And you see it's a fraction of 67%. So 67% of your magnetic energy at the CMB is contained in an axisymmetric dipole. This means that your solution is really dominated by a dipole. So that's already from the time series, you can have an idea on how the solution looks like. So of course, my time series again is very short here. I just run 10 times step or so. So you should have something more fancy with the transient phase at the beginning.
There's no underscore.
So you have like, well, I think for the time being, that's the three files which are interested for you. So Ekin, IMAG, OC, and PAR. So kinetic energy, magnetic energy, and diagnostic parameters. That's the three files that you may want to look at for first thing. Okay, now you look at your solution. It's probably for most of you, the run is over now. So you may want to look at how the solution looks like, right? And to do that, you can load the file I suggested here. So the surf is actually trying to read some files named capital G underscore, then a number, dot test. So the IVAR here gives the number. So if you want to read the first one, just type 1. If you should have 3, I think, in your directory if the run finished correctly. So if you don't put this IVAR, it's going to try to read the latest. So it's just an optional parameter here. So if you just put s equals surf, it's going to try to read the latest. I can show you here. So it's going to be s equals surf. And then it's reading the latest one. Okay, so now you have 3D arrays. So you can do some possible visualization on that. So you can think about doing some equatorial cuts of your data, doing some azimuthal cut of your data, or doing some radial cuts of the data. That's the most common thing you can think about. But you can also think about averaging in a 5 direction, which is also very standard if you want to look at your axisymmetric structure of the field lines or whatever. So here are a couple of examples for if you want to display an equatorial cut of the R. So you just type that, and it's going to display an equatorial cut of VR, which is here. So, so you have some amplitudes that you can see here. And this amplitude, what does it mean? As Johannes explained, the code works in dimensionless units. So what is actually, the quantities that you see here are Reynolds number. So, so V is expressed in Reynolds number units. So when you have 20, it means that the Reynolds number is 20. So what you see in the equatorial cut is 4 pairs of columns, as Uli showed. So you can imagine that these columns will be fairly aligned with the rotation axis. And this is just an equatorial cut. So you have always like an upwelling associated with a downwelling, and you have that 4 times. And you also notice right away that it has perfectly 4-fold symmetry. So the solution you could just run on the quarter, then it would be exactly the same solution because it has, well, this solution has perfect 4-fold symmetry. So it's perfectly symmetric. Well, you can tune your plot if you don't like the color or whatever. I'll just show you briefly. So you can change the color map, whatever. And you can increase the number of levels as well. Yeah, increase it if you like. So let's put 6500. Yeah. And then, okay. It's hard for me. And here you go. So you get your 65 levels now instead of whatever. So which can be useful if you have very small scale, then obviously the default number of contours won't display them, so you might need to tune that depending on your solution. I mean, on the benchmark here, it's very large scale and so forth and so on, so you don't need to really tune your parameters too much, but in case it's becoming very small scale, you might need to adjust a little bit your visualization. There are also some ways to truncate your control levels. If you want just to display from -10 to 10, you can do that. So there are a big bunch of options that should be either on the manual or here, hopefully. Let's see. Yeah. So I just give some example in the documentation, and you have all the parameters, all the possible options that are displayed here. So you have a lot of them. So you can always access the documentation by just typing pdoc and then the name of the function, and it kind of gives you the documentation, which is the same as in the manual. Right? The manual is a new build. So okay, so that's all for equatorial cut. So the interesting thing here is to change the quantity you may want to display. So I don't know if I want to display instead. Well, I don't know. If I want to display PR, for instance, let's display PR. So this is just the radial component of the magnetic field. And B5, or you can access any component of your thing. So B5, for instance, you get the BP here. Or actually, B5 should also work if I did my job correctly. Yeah. So I mean, it should be pretty clever regarding the naming here. So whatever you type here, even if you put a capital, it should make it. Yeah. Right. So it's you don't need to remember the exact syntax here. It should more or less do it if you have something which makes sense, right? If you don't type it, yeah. B5, B theta, BR, BR, B theta, BR should work. You can also plot the temperature or the entropy, so the same way. So it's just the temperature fluctuation, so it's just a hot upwelling here, and then the cold thing.
Yes.
Okay. So that's approximately it for equatorial cut, I think. But you have a lot of fields that you can display, like vorticity and things like that, which you can play with. But I won't show it here. So the second thing you can plot is the radial cut. So let's do it. So here I plot the radial component of the velocity. And I have to specify at which radial level I want to cut. So this is the point of this parameter R. And this is given in a fraction of the outer radius. So if I put 0.8, it means that I'm 80% of the outer radius. If I put 1, it's going to be exactly the outer radius, so the CMB radius in that case. So you see this kind of plot. Again, we find with 4 pairs of columns, with these upwellings, downwellings, that we already had in the equatorial cut. Just confirming. Still here. Again, you can play with the number of contours and whatever if you want. And you can plot it for different radii, so you can get closer to the surface. You see quite a little bit of different structure. So in this peculiar solution, one thing interesting to look at is the magnetic field, the radial component of the magnetic field, BR. And BR, you want to plot it at the CMB radius, so you just put R1 here, and then you're going to have that. So it's fairly dominated by a dipole. And on top of that, you see this signature of your 4 columns, which give these 4 full patches that you can see around maybe plus minus 60 degrees. So you have these patches here, these red patches and the blue patches in the northern hemisphere. So that's how BR looks like. And again, you can do the same thing for the different components, so B5, B theta, and whatever you want to plot here. Okay. So it's by default it's plotted on the hammer projection. You can change the projection, but for that you need an additional library which is not installed on the cluster. So I won't show it today, but in principle you can change the projection if you want to go like orthographic projection or whatever. You can do it. It's no problem. Okay. Then the third thing you may want to look at is the phi average. So it will give you a plane or a 2D plane, theta r plane, which will display the axisymmetric component. So if I do that, for instance, I will display the toroidal axisymmetric zonal flows. So this is basically the differential rotation, if you want. So in red, it's prograde into the board, to retrograde towards us. So you have some, well, you have some differential rotation structure here displayed. So at first glance, you can say, wow, it looks like you have a lot of structure in there, but keep in mind that the amplitudes are very tiny here. Look at your amplitude here, you have around 4, 3, 4, so your Reynolds number is very tiny, so which means that this axisymmetric zonal flow is pretty small here in this, as compared to the non-axisymmetric contribution. So this is for V phi, and you may want to plot BR, for instance, if you want to see the axisymmetric radial component of the magnetic field. That's what you get. So it's a fairly dipolar structure with some contribution of the optical that you can see. Close some of those. Okay. So you might want to plot B phi. So this is the axisymmetric toroidal magnetic field, so B phi axisymmetric, and you might want to overplot the toroidal field lines in there. So you just do probably put through and it's gonna do it. Search me. Shit. Where am I? Here. Yeah. So here, what you see. Yeah. So now you have your axisymmetric toroidal component of the magnetic field color-coded. So red into the board, blue towards us. And on top of that, you have the poloidal field lines plotted in dash here. So you find the dipolar structure. Yeah, it might be because they use symmetry or whatever. Or it's
What is
it's blank. It's like full symmetry. Oh, it's just B phi, symmetric B phi plus poloidal field lines.
Yeah, otherwise it's spectral. What is the spectrum?
Okay. So that's already something to look at your solution. So you can also do some slices using the S-dot slice, which is, well, you have to specify the longitude at which you want to slide. So let's say I want VR at a longitude of 0. I have to get something open. Oh, it does that. Well, there's a little error here, so I don't know. But I mean, yeah, just controlling the display. So you can display it for several longitude if you want, like 0 and 30 degrees. Yeah, 0 and 30 degrees. No, it's just because it's 4 zeros and it's going up scale, so just display it in upscale. Because it's exactly 0, so
Yeah.
plus
Yeah.
here as well. Minus 30.
So the problem is just one way.
Click
That is a 0. So in log scale, you can't show anything.
Okay. Okay, so now the last step is, okay, now let's suppose you want to visualize your solution in 3D. Then you have to do some additional steps. Go back here. So you have to load your graphic file and you have to convert it to a format which is readable by ParaView or any software that supports VTK. So it can be ParaView, Visit, Mayavi, or several others. So to do that, you have to convert the output of Magic into this file which is readable by ParaView. So it's just a two-step thing. So first you load the graphic file, and then you pass it to this routine, which you should have. And you should produce a file which is named output.vts. And this file is going to be loadable by ParaView. And ParaView will allow you to play with, fill lines, 3D rendering, and things like that. Produce a VTS file. Yes, but only when you do that, right? You want to grab VTK. And you use this command.
Oh. Not defined. Graph to VTK. Ja, du kannst dich nicht als gut anmelden. Weil Ubuntu sperrt rot. Ach. Aber ich kann das noch nicht genau, so geht. Ja, und dann in den Bot in die Ach, das geht, na dann passt es doch. Dann sag einfach, dann setzt das Sudo mit. So. Okay. Ja, genau das Ding hier ist eigentlich. Ich habe ausgesehen, dass es bei was ja,
You can change the axis if you want to make it where you are.
Das ist ein krasses Programm. Das warte ich die ganze Zeit, wie das geht. Und jetzt geht's. Alles geht. Krass. Das funktioniert fertig. Nein, was hast du denn anders gemacht? Krass, 2 wichtig.
Aber der findet da diese Motive da gar nicht.
Ja. Name graph to VTK is not defined. Du musst erstmal gut gewählt sein, das ist richtig. Ach, bist du, okay, ja. Wo steht das jetzt noch? Der
So let's take the magnetic field. So by default, comparing that, creating some points and trying to figure out what are the 100, and it's moving randomly within the sphere of 0.3. The thing is that here the domain that you have goes in radius of 1.5. So you rather use 1.5. So far it doesn't very good. Make your line so your gallery is like that. Nice to take. So that's just very good. Okay. So what you can do is vary
Wie kann ich das machen? Remote.
Which means that if you like to take it's more than you want to
I never use part of the
File. Ja, Mount wieder so. Nee,
because without the chart.
yeah. Ja,
Wow, it's a crazy solution. Oh my gosh. That's your final step. Because you create your okay. Because you're okay. Okay. Yeah, I think. Let's see if I can make it on my laptop as well. Yeah. So it's actually more I'm not updated. Yeah.
Everything works except graph to BTK.
Which means that you didn't build the library, so not everything works. So do you have a Fortran compiler? So let's go on that.
Is there a reason why?
Yeah, there is a reason.
Oh, okay.
There is a good, very good reason. It's just not sure twice in this part here, so it requires a Fortran thing. Why is it?
Here, magic. Yeah, master.
See? I mean, usually you don't. If it builds properly, it should have some .so file. Also, which means that this file here was correctly done. Did this set no here? So we have a file. Yeah. Okay. Figure that out. Usually it builds it with, well, let's try it. So let's remove this file and let the system build it for you. So what I do is just source the file. Now I should have produced the file, I just delete it and set it as correctly according to what it found. So, yes, modify the compiler because we didn't write it. Now, next step, go to IPython, practice shell. As you can put star, it's just a warning, but now it's building the library. Which also means that the reading of the graphic file is going to be much faster because now it's like so I suppose when you source the source me the first time, you may not have some Python or some yeah, right. So now it should work. Or I don't know what you create. Now the series of commands should work.
All right, thanks. Sorry. What's contained? Sorry. The scatter and so yeah, radius, velocity, magnetic energy, fluctuating entropy, scatters, and execution velocity, and
so there's no
yeah, you can. Yes, you can. But by default, it's just trying to. There is a default list of scatters. You can expand this list by adding some option. So there is like the graph to BTK.
So there should be also the magnetic field.
Yeah, I don't know why it's not there.
Because I switched it off.
Yes.
Ja, ja. Wir nehmen das jetzt für Gaia auf.
Okay.
Weil nicht
abstimmen.
Du kannst doch vorne diese Kurve. Ja, oder? Weil das schön erklärt ist.
Die Doku.
Ja, gewählt.
Wie ist auch nicht.
Oh, ach, die ist hier. Ja.
This is now one.
So I have the file ready.
Okay.
Yeah. What is remaining for you? Nothing, right?
No.
You're done.
So, so either you can tell and I can do it, or
I can do it. Okay, so where I am here. So you loaded the data? Yeah. So the first thing you can think about is doing some contours of scatter data. To do that, you use the first thing here. And here you are in this panel, and you have different options. So here it will list the available scatter that have been stored in the VTS file. So I don't know, let's take, for instance, radial velocity. And here you can choose the value you want. So you see the range, it ranges from -20 to 23, again in units of the Reynolds number. So you don't want to take these extreme values always, well, it's just localized points which will reach this value. So let's take, I don't know, 5 or so. And apply. Okay, now you have your columnar structure. So how do I know where I am? You can use these little things here. So if you use the +z or the -z, it means that you have either a top view or minus view. So you're looking, I mean, the rotation axis is into the board just or towards you, depending if you use +z or -z. Yeah. If you use the x or the y, then you're looking on the side view. So it's basically the equatorial plane. Okay, now you want to display maybe your couple of columns. So you want the negative value as well here. So you do add value, and you just put -5. That's nothing really complicated. You apply, and you do something. Yes, now I have pairs, but I don't know which one is which one here. So you need one step more. So you can color, I mean, to change the color by the value, you use this coloring option here. And these coloring options, by default, it gives me these options. So velocity, well, all my scalar things, except VR, which I'm interested in, because I want to display the value of VR here. So to do that, I just tick here this compute scalars option, and I apply. And I just say I want to color it by the value of VR, which I do here. And here, radial velocity. And here you go. So now you have in red your upwellings, in blue your downwelling. Right. So that's the first thing you can think of. Okay. The second thing is, of course, streamlines, because you may want to display, for instance, either the magnetic field lines or the flow field. And to do that, you use this one, which is called Stream Tracer. So you click on it. And the first option you see is the vector field you want to display. So it's either magnetic field or velocity. So you take magnetic field here. So you don't touch that. It's just advanced options. So what ParaView does is that it's spreading some random seed points throughout your domain. And for each of these seed points, it's trying to find the field or calculate the field lines which passes through the seed point. So you have to, well, by default, it's just like putting some random seed points throughout the domain or throughout the spherical domain. And this is the radius it picks up by default, so 0.3. So obviously here there is a little issue because the spherical shell ranges from 0.5 to 1.5. So you have to increase this value, let's say, to the outer radius. So 1.5, let's say. And this is going to be the number of field lines. So let's put it to whatever, 200. And let's remove let's command the contour. So to hide something that you calculated, you just use this one here, and then it's in, right? So you can restore it for us. Right? So no, I go back to my stream tracer. 1.5, 200 points. I apply here. Okay. So it doesn't look very good yet, but there are some tricks.
there are some tricks to improve that a little bit. Especially you can, I mean, so far it's just lines and you want to make them thicker. So it's a bit advanced preview feature. So you go to filter, alphabetical. Well, only first time alphabetical because then, and you use two. Okay. So let's do it by default and apply. Wow, I got this spaghetti monster stuff. So it's obviously slightly too thick. So I want to make it, you know, thinner. I go to 0.1 here. Why not 0.1? Okay. So it looks a little bit better, but still it's not really convincing because what you want to highlight is the region where you have most of the induction. And Purview offers a very nice feature here. It can vary the thickness of your field lines by some scatter. And that's what we're gonna do here. So vary radius here, we turn it to on and we set by scalar. So which means that the size of my field line is gonna vary by scalar. And I have to choose which scalar I want. So you see that here by default is angular velocity, which doesn't make sense here. So rather use magnetic energy. So why magnetic energy? And what does it tell us here? It tells us that the thickness of the field lines will depend on your local magnetic energy. So if you have a strong magnetic energy, you're gonna have a strong field lines, thick field lines. If you have a local region where magnetic field is very tiny or very small, then you're gonna have very tiny field lines. So it's gonna emphasize the place where the magnetic field is particularly strong. So let's do it like that as a first shot. Biscalar, and the radius factor means the factor between the thinner field lines and the thicker field lines. So let's apply. Okay, so I get something like that. It's slightly too thick, I would say. So I can reduce this guy here to maybe 0.03, whatever. Okay, and what I can even do is increase the factor to emphasize a little bit more the ratio here, and then I end up with another trouble here with thickness. Right. Okay. So it starts to look decent. Now you really see the region where that Uli was mentioning. So we are a bit lost in the sphere, so why not adding the inner sphere? So how do I add the inner sphere? I just do a contour and I put radius. Radius, and I say, radius. And I want the inner radius, which is, as you can see here, 0.538, whatever. So let's put 0.54 here. Okay, it's just a warning message, no problem. So now I have my inner core. Right. So what I can do as well is I can color my tube with the magnetic energy, for instance, and then then you start to see something which looks better because now it's clearly emphasizing the region where you have strong magnetic field. So you can even think about going to a bit more streamlined to make it even better here. Okay, here you go. So now it looks decent. Okay, so what else can we do? We can possibly say, okay, why not plotting an equatorial cut? So how do I do an equatorial cut? I just do a slice. And so the slice is doing that by default. So what you want to do is an equatorial cut. So you want a cut which is perpendicular to the z-axis, which is the rotation axis here. So you click here. And, well, what did I do here? Yeah, I think it should be fine. Okay. So what do I want to display here? So what do I want to display in this plane? I don't know, radial velocity, whatever. And I don't want to show the plane. I don't want to see this plane, which is just useful for plotting at the beginning. Right. Oh, that's one set. Show center. Okay. Well, and then you can put some transparency, some fancy stuff if you want. So, Well, that's about it. So that's the three tools you may want to use: slices, contours, and streamlines.
Auch cool.
Yeah, the streamlines, you have to make sure that you use the number. The only tricky thing with the streamlines is where you locate your seeds, and this is controlled by this radius here.
Yes, but I click on a point is defined differently. That doesn't matter. Okay, that's not difficult. And then the maximum length is that important.
Well, you can play with that in case it doesn't look very good, but usually I leave the default thing.
Position und
1.5, and then I say apply, and nothing appears.
So I don't know if it will work fine if I combine the thing here.
oder
Let's try.
die Zeit.
Oh yeah, looks decent. So I can even put some transparency on the initial contours, and okay, I don't want to overemphasize them, so I just change this opacity here to maybe something like that. Okay, and then you may not like the bluish background. I don't know if it's going to look much better though, but you just go to view settings, choose color, you pick a black, you apply, and you're done. And here you go. Well, it looks like a bit fancy here now. Yeah. So now you see your like here it's very nice because like if you take these pairs of columns, you exactly see what Uli's sketches this morning. So you have like the pairs of downwelling and upwelling, and you really see the stretching, twisting happening between the columns here, just in between the columns here, and then in the azimuthal direction in the top. So it's very cool. It's really reproduce what Uli showed this morning here. So we're quite happy. So you might have some advanced thing on the rendering as well. So maybe I can show it. I don't know. That's gonna work. I think you can edit the color. No. Two.
Bei dir
Okay, okay, that's the old version.
Sogar noch 4 Minuten. Genau, da.
There's something like that. But I don't know.
Ich habe hier unten noch. Nee, ich glaube hier unten.
It's pretty cool now because my field lines themselves are transferred by color a little bit. So well, at least it should be. If it's reddish, it's more visible than the bluish, so that's exactly what I'm after here. So you can play with that as well in driving. That's pretty cool. Okay.
Ja, du kannst ja noch die Anzahl der Linien
Yeah, what is radius? So you just pick up radius here. And you put point 0.54 because usually if you put 0.53, it's below the domains and won't display anything. So around that, upper around it or whatever. And you will display 1 Newton.
Das kann ich vergessen.
Nice. So I did some fancy additional thing with the transparency of the lines, so you can tell Paraview to make, so you can use that universal opacity mapping for surface. Sometimes that is something. Update. So sometimes, I mean, that's for instance what I use for the MRI from so that you have this, you see the inner structure of the look, but it may look better on the black background.
Das ist nur die Range. Du stellst jetzt quasi die Radial Velocity mit einer Limit von 5 dar. Das ist eine Surface.
Radial velocity.
Wenn du das runternimmst, oder höher nimmst.
Yeah. Okay. Well, you can do a trick and add in the VR within the scanner. So you grab the BTK, you can leave the scanner if you want, and then you can add VR.
Ich zeige deine Tubes weg, ja, das liegt da ran. Positiv. Geh nochmal zu den Konturen. Und schick hier mal plus.
You can do the potential field extrapolation as well.
Und jetzt mach mal Minus.
Not here, but you're doing the graph to BTK phase, you can generate it. Yeah,
Range.
pretty cool.
Genau. Ja, der fährt jetzt, also das ist Cover jetzt, der fährt die nach Geschwindigkeit an.
Genau. Aber nicht nach die Meinung bei ihm ist ja irgendwie das hat er
Energy. Entropy.
Yes, yes, of course.
noch? Also,
Ja, du kannst auch noch Color.
ja, ich sehe der Color schon mit drin, aber kann man da den Range irgendwie verändern? Das ist eigentlich das große.
Nee, auf das daneben. Schiebst du mal auf das Herz zu. Ja, rechts, ja.
Da kann man einfach so gerne das Color lassen. Und hier kann man
Und da kannst du noch Intensität und sonst so.
Ja, eben.
Meine Spaghettis variieren nicht.
Hat sie nicht entwickelt, weil wir.
Ja, das sind immer gleich.
Hast du den Radius mal
Gleich, weil die alle, wo ich sage, bei Scaler.
Ach so, dass die alle
Vektor 10. Ah ja. Na, da kannst du die Reaktion der Dicke ansehen auf das Skala ändern. Ich habe damit auch mein Mars-Video gemacht. Ich war auf YouTube.
Ja, ist das dann? Also ich meine, bei Marken,
Das ist den Motor und Kraft.
ja.
Mars Convection Ratio. Ja, es ist weiter.
Kann man dann, kannst du dann auch
Ja, da kannst du auch noch messen.
wir können auch mal
Du arbeitest ja nur remote, glaube ich, auf dem Ding. Ich wundere mich, dass es überhaupt geht.
Oder alles für uns aus dem Code, ja.
Das sieht nur so die Nische aus.
Macht schon was her.
Das war schon mein Test.
Okay, now we have.
Und da dachte ich mir, das war eigentlich so.
Ja, ja, ich sag es auch.
There, it's difficult.
Genau, das ist YouTube-Channel, wo immer mal Connection-Channel
But no, it has it out.
nicht halt so.
Now what's left? Ah, you want to have there is also the coloring of the outer has also affected. But the few lines are not. The few lines are awesome. Yeah.
Dann geh mal hier runter. Wir haben nicht Surface, sondern ja, das steht noch das kosten kurz. Ja, und die implementiert gegen Geld als Features, wenn du uns brauchst.
Aber die stellst du dann immer zur Verfügung für alle oder halt dann?
Nee, das.
Wenn du es bei dir reingibst, und du denkst,
If I make it
ja,
overlap, where they overlap, the capacity is this one.
Genau, aber du musst ja auch sehen, wie viel musst du dir vorher haben, bevor du das einmachst. Das hat unsere Studenten halt einfach, hier baut einfach sagen, in dem Verzeichnis meine Information machen.
Ja, lad rein und dann.
Und dann kannst du nämlich auch diese Knöpfe hier oben verwenden und kannst eine Zeitreihe noch mit verwenden. Das heißt, du kannst eine Zeitreihe
Yeah, additional stuff you can do possibly with the graph PTK options.
Ich glaube, du musst noch 100 andere.
Wow.
Sehr schön. So, was haben wir noch gebraucht?
Well, it's just to show you know now.
Dieses Bild, was wir nochmal löschen, dann nochmal erstellen. Denkt dann, ja, achso. Hast du ihn nicht gefunden? Was? Oh mein Gott.
honest, can you decrease the y? Or how do we do that?
From the maybe do Alice house.
What do you want? I want to shoot something else. The one last thing we can do with this graphic output, so maybe you could increase the size of your channel.
Yes, I'm looking for my cursor.
Over here.
No, my mouse. Yeah.
No, I want to see it right now. So load the graphic.
Yeah, it's already.
Okay. The graphic.
Look, I think it takes this ISO surface and either makes it through a color that cuts the ISO surface. You can plot something, but then it's an ISO surface. It's just plotting like, okay, now I'm going to this one. But you actually don't.
And then you put the list of scanners you want.
Okay, I think we put it quite high.
Scales equal.
Yeah.
No scale.
Okay. Yeah.
So what's their plan
Well, I
for?
just wanted to show it. So a few stuff. Then put the list.
Like a list.
Yeah. The BR, just put BR. Just put the potential. And then put
Extra.
yeah. All right. So just check that it was released channel. Oh, go to see
But it becomes something.
I don't know. Whether now you works, so load it and buy.
Yeah, it's just a velocity.
Yeah, but there is no scatter. So yeah, so it's fully scattered and scaled.
Okay.
Just do it again. But you have the potential. Scattered.
Oh, nicht auf die Kontur. Genau. Und jetzt.
I was thinking of what's the name of it?
Ja. Jetzt müssen wir noch warten. 1,6.
Or maybe PR. Well, I mean, it's just straight.
So you do expenses or do you?
Yeah, yeah, just streamline extrapolation. VR doesn't exist. Yeah, just show the option. Go back to those things. VR doesn't exist. VR. Yeah, VR and
Da gibt es noch die Benchmark 1.
but I know what you show.
Der hat auch diese kleine
Okay, so switching up.
VR.
Because this
Also das Verhältnis innere Kernleitfähigkeit und äußere Kernleitfähigkeit. Da kannst du auch mit einer Regelzahl von 10 auf 5 festlegen. Aber wenn du die innere Kernzahl nimmst, 10 auf 5 festlegen, kannst du darum. Weil der innere Kernleitfähigkeit ist mit der Summe
Show the graph.
da musst du die Regelzahl bis zu hier setzen, damit du noch
Okay, so one last thing you can do. So when you're doing this graph to VTK, there are some additional options that allow a better control on which scalar are actually stored with your file. So here it's just an example where you can list actually the scalars you want to have in your file. So here, by default, so by default, as you saw, it's storing like entropy fluctuation, VR, and so forth. So in case you want only VR, it might make sense just to pass this list here. And the second option is actually pretty cool. What it's doing here is just doing a potential extrapolation of the field lines outside the spherical shell. So if you want to have your nice dipole and see that like the field lines closing outside, then you can use this option here, and then you're going to see your field lines closing outside of the domain. So it's just quite extra for potential extrapolation. So it will produce a new file, and you can use this file again as part of your manipulated data. Somebody's head about the
maybe you had it.